This section is about frameworks and internal forces such as tension and compression. So you want to build a bridge out of string. Is it possible? Or is it a stupid idea? Well, and this is often the case in engineering, it depends. It depends on the shape of the bridge because this dictates where the forces act on the bridge and, by extension, the way that the forces are distributed within it. The main two forces that bridges can experience are tension, bits of the bridge being pulled apart, and compression, bits of the bridge being pushed together. If we consider a very simple bridge, a plank of wood spanning a river, then we can see which bits are in tension and which bits are in compression. The bridge is supported at either end by the riverbank, and it bends downwards in the middle under its own weight. The top of the bridge is in compression, and the bottom is being pulled apart, it's in tension. There are two iconic shapes of bridge which demonstrate tension and compression very well. First, an arch bridge transfers all its weight and the weight upon it downwards and outwards to its supports. It's being pushed together and is everywhere in compression. This bridge should be made out of a material which is strong under compression, for example, concrete or masonry. Second, a simple suspension bridge is anchored at each end and hangs under its own weight. It's being pulled apart and is everywhere in tension. This should be made out of material which is strong when in tension. For example, string, rope or steel cables. The type of bridge that we're interested in fixing with string is one which is made up of a framework of interconnected elements or members and is called a truss bridge. A truss bridge is made from a triangular framework of elements. All the elements have forces on them and are either in tension or compression depending on where they are in the network. We call elements that are in compression struts and elements that are in tension ties. We could, in principle, replace the ones that are in tension with string. Let's consider which elements these might be. First, let's think about the external forces which are acting on the bridge. These are its weight, and this is balanced by two reaction forces where it is supported at either end. Because the bridge is in equilibrium, we can balance the forces at any joint in the network and then see which elements are in tension and which are in compression. For example, the leftmost joint must contain a strut to balance the upward reaction force, and then a horizontal tie to make the overall force zero. For the bridge as a whole, we find that the bottom of the bridge is in tension and could be replaced with string. The top of the bridge is in compression and could not be replaced with string. The middle of the framework alternates with struts and ties, meaning that we could feasibly replace about half of the elements with string, and thus extend the bridge across the whole river. The main internal forces which act on bridges are tension and compression.